Consider this. We can photograph galaxies billions of light years away. We map the spiral arms of distant nebulae. We watch supernovae explode halfway across the observable universe. Yet the most gravitationally powerful objects in existence remain fundamentally invisible, not because they're far away, but because their very nature prevents light from escaping their grip. Throughout the cosmos, in the hearts of galaxies both near and distant, these objects exist in staggering numbers. At the center of nearly every large galaxy sits a supermassive black hole. The Milky Way weighs 4 million solar masses, others reach billions. Stellar mass black holes, the collapsed cores of massive stars, drift through interstellar space in quantities we're only beginning to estimate. Some models suggest millions in our galaxy alone. These aren't voids or vacuums despite their name. They're regions where matter has achieved such extreme density that space-time geometry warps beyond recognition. The gravitational field becomes so intense that it creates a boundary, the event horizon, beyond which the escape velocity exceeds light speed. It's a point of no return encoded in the structure of space-time itself. Tonight, we're pursuing a question that bridges physics and philosophy. Not the mechanics of formation, though we'll explore stellar collapse. Not their observational signatures, though we'll examine humanity's first photograph of an event horizon. Not simply their properties, though we'll work through the mathematics. We're asking something more fundamental. Why do black holes exist? Not mechanistically what creates them, but ontologically. What makes them necessary features of our universe rather than mere curiosities? Do they serve functions in cosmic evolution? Are they unavoidable consequences of physical law? Could the universe exist without them, or are they as essential as atoms, forces, and space-time itself? This investigation will take us from stellar death throes to space-time mathematics, from gravitational wave detections to quantum paradoxes. We'll examine black holes as galactic architects, as thermodynamic systems, as rotating geometries that drag space-time itself. We'll consider their cultural resonance and their ultimate fate trillions of years hence. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Your presence here, whether you're listening in the quiet hours before dawn or in the peaceful moments before sleep, it matters more than you know. Now let's begin with a star running out of fuel. Picture, if you will, a star. Not just any star, but a giant one that outweighs our sun by 20 times, 30 times, perhaps even 100 times. This is no ordinary point of light in the night sky. If you could somehow stand at a safe distance and observe this stellar leviathan, you would see something magnificent and terrible, a sphere of plasma so vast that if you placed it where our sun sits, its surface might extend past the orbit of Mars, perhaps even Jupiter. Its luminosity would dwarf our sun's output 10,000 times over, a blazing beacon visible across vast reaches of intergalactic space. For millions of years, perhaps tens of millions depending on its exact mass, this star has been locked in a delicate balance, a cosmic equilibrium between two fundamental forces that have been at war since the moment of its birth. It's a battle as ancient as the universe itself, played out in every star that has ever burned, is burning now, or will burn in the distant future. Outward, from the very core of this massive star, nuclear fusion pushes relentlessly. Deep in the central furnace, where temperatures reach tens of millions of degrees, hydrogen nuclei overcome their natural electromagnetic repulsion and fuse together, forming helium. This process, the same reaction that powers our own sun, releases tremendous energy. Photons born in these fusion reactions begin a long, random journey outward, bouncing from atom to atom, taking hundreds of thousands of years to travel from core to surface. This constant flood of energy creates an outward pressure, radiation pressure, and thermal pressure combined that pushes against the star's own immense weight. Inward, gravity pulls ceaselessly, inexorably. Every atom of the star attracts every other atom. The cumulative effect of trillions upon trillions of tons of matter, all pulling toward the center, creates a crushing force that would collapse the star instantly if not for the nuclear furnace at its heart. Gravity is patient, constant, never tiring, never yielding. It has been trying to crush this star since the moment the star first coalesced from a cloud of hydrogen and helium billions of years ago. These two forces, expansion and collapse, nuclear fire and gravitational weight, create an equilibrium, a temporary peace. A balance so precise that the star maintains nearly the same size for millions of years, neither expanding significantly nor contracting, simply existing in this perfect tension. The star shines steadily, a beacon powered by the essential struggle that defines its existence. The clock ticks differently for stars of different masses. The universe moves forward, entropy increases, and stellar fuel depletes. The process of stellar aging is written in the language of nuclear physics, a story told through the periodic table of elements. Our massive star begins its life with a core of hydrogen, the simplest and most abundant element in the universe. For millions of years, it fuses this hydrogen into helium. This is the main sequence phase, the long, stable period that defines most of a star's life. Our own sun is in this phase now, has been for about 4.5 billion years, and will remain so for another 5 billion years or so. But for a massive star, this hydrogen-burning phase passes much more quickly. The more massive a star, the hotter its core must be to generate enough pressure to support its enormous weight. And the hotter the core, the faster the nuclear reactions proceed. A star, 100 times more massive than our sun, might exhaust its core hydrogen in just a few million years, a cosmic eye blink compared to the sun's 10 billion year main sequence lifetime. The temperature requirements escalate with each new fusion stage. Hydrogen fuses at 15 million Kelvin. Helium requires 100 million Kelvin. Carbon fusion needs 600 million Kelvin. The stellar interior becomes an inferno beyond comprehension, with each successive shell of fusion occurring at temperatures that would have incinerated the previous generation of reactions. The star develops an onion-like structure, with iron accumulating at the center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen at the surface. Each shell burns at its own characteristic temperature, each contributing to the star's luminosity, each racing toward exhaustion at an accelerating pace. When the hydrogen in the core is exhausted, the star faces its first crisis. The nuclear furnace dims, the outward pressure decreases, gravitational compression takes over. The core contracts under its own weight. This compression heats the core, and when it reaches about 100 million degrees, hot enough to overcome the higher electromagnetic repulsion between helium nuclei. Helium fusion ignites. Helium fuses into carbon and oxygen. The star has a reprieve. The nuclear furnace roars back to life, and for a time, equilibrium is restored. But this helium-burning phase lasts only a tenth as long as the hydrogen-burning phase. For our massive star, perhaps a few 100,000 years. And then the helium runs out. The core contracts again, heats again, and carbon fusion begins. Carbon fuses into neon, sodium, magnesium. The timescales grow shorter. The star is burning through its fuel faster and faster now, like someone trying to keep warm by feeding a fire that's running out of wood. The core grows hotter with each contraction, reaches higher temperatures, ignites heavier elements. Neon fuses into oxygen and magnesium. That phase might last a few years. Oxygen fuses into silicon and sulfur. That phase might last months. Silicon fusion, the final step, produces iron. And silicon burning might last only days. Days. After millions of years of stable hydrogen fusion, the star reaches a point where it's consuming its remaining fuel in mere days, racing desperately toward an ending that cannot be avoided. And then, inevitably, irreversibly, the core fills with iron. Iron is the end of the line, the point where fusion becomes a losing proposition. You see, all the fusion reactions up to this point have been exothermic, meaning they release energy. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. Even fusing silicon into iron releases energy. But iron sits at the peak of the nuclear binding energy curve. Fusing iron into heavier elements requires more energy than it produces. It's endothermic. The nuclear fire cannot burn iron. There is no fuel left. The core, now composed of iron and nickel, has reached a point of no return. It can contract no further and ignite a new fusion process. The outward pressure vanishes almost instantly. Gravitational collapse proceeds unchecked, catastrophically. What happens next unfolds in a time shorter than it takes to blink. The iron core collapses, not slowly, not gradually, but catastrophically. In less than a second, the core, which may have been about the size of Earth, implodes to a region perhaps 20 kilometers across. The density skyrockets to values that defy everyday comprehension. A teaspoon of this material would weigh more than Mount Everest. Electrons are crushed into protons, forming neutrons and releasing ghostly neutrinos that pass through matter as if it weren't there. The temperature spikes to hundreds of billions of degrees, hot enough that thermal photons have enough energy to disintegrate iron nuclei back into their constituent protons and neutrons. The infalling material rebounds off the incredibly dense core, creating a shock wave that races outward through the star's outer layers at 30,000 kilometers per second. But the shock wave initially stalls, trapped by infalling material and energy losses to neutrino emission. For a crucial fraction of a second, the star teeters on a knife's edge. Will the shock wave revive and blast the star apart, or will it fail and allow all the material to collapse into the core? In most cases, neutrino heating revives the shock. A tiny fraction of the flood of neutrinos emerging from the core deposits energy in the material behind the stalled shock, reheating it, giving it the boost needed to blow the star apart. This is a core collapse supernova, one of the most violent events in the universe. The shockwave blasts the star's outer layers into space at speeds of 30,000 kilometers per second or more. For a few weeks, the dying star will outshine its entire host galaxy, blazing with the light of billions of suns visible across half the universe. New elements, forged in the incredible heat and pressure of the collapse and explosion, are scattered into space, gold and silver, uranium and platinum, all the heavy elements that make up planets and life itself, born in these cataclysmic death throes. But we're not concerned with what's blown away. We're interested in what remains behind. For most core collapse supernovae, the remnant is a neutron star, an object about 20 kilometers across, but containing more mass than our Sun, a sphere of matter compressed to nuclear density, where a teaspoon of material would weigh as much as a mountain. Neutron stars are extraordinary objects in their own right. Laboratories for exotic physics, pulsing beacons that sweep radio waves across the cosmos. But if the progenitor star was massive enough, if there's enough material left in the core after the explosion, even neutron degeneracy pressure cannot hold. There's a mass limit discovered by physicists in 1939, above which no known force in the universe can prevent further collapse. That limit is somewhere around 2 to 3 times the mass of the Sun, the exact value depending on the equation of state of nuclear matter, something we still don't completely understand. Above that threshold, collapse continues. The neutron star cannot support itself. It shrinks further, becoming denser and denser. As it shrinks, the gravitational field at its surface grows stronger and stronger. At some point, the escape velocity from the surface reaches the speed of light, and then it exceeds the speed of light. At that moment, a surface forms in spacetime. Light itself, traveling at the ultimate cosmic speed limit, cannot escape from within this radius. Anything that crosses this threshold is lost to the external universe forever, causally disconnected, unable to send signals outward, unable to influence events beyond. This surface is called the event horizon. The object that has formed is a black hole. In 2024, astronomers studying the system, a stellar mass black hole, made a remarkable discovery that challenges this picture. This stellar mass black hole, located about 8,000 light-years from Earth in the constellation Cygnus, appears to have formed through direct collapse, skipping the supernova phase entirely. A stellar mass black hole is in a binary system orbiting a companion star, and careful observations of both the black hole's properties and the composition of the companion star revealed something unexpected. The companion shows no signs of having been contaminated by supernova ejecta. If the black hole had formed through a normal core collapse supernova, the explosion would have blasted the companion star with heavy elements, leaving chemical signatures we could detect in its spectrum. Those signatures aren't there. Instead of exploding outward and leaving a remnant behind, the evidence suggests the progenitor star simply folded in on itself, collapsing directly into a black hole without any violent fireworks to announce its transformation. The outer layers of the star, instead of being ejected at tens of thousands of kilometers per second, simply fell inward, adding their mass to the growing black hole. From the outside, the star might have simply dimmed and vanished over the course of days or weeks, collapsing into invisibility without ceremony, a quiet death instead of a spectacular one. This direct collapse scenario might be more common than we once thought, especially for the most massive stars. When a star is sufficiently massive, more than perhaps 100 times the mass of our Sun, The core may become so unstable that it implodes before any shock wave can form. Or the shock wave forms but stalls deep within the star, unable to fight its way out through the enormous overlying weight of the star's outer layers, which can amount to dozens of solar masses pressing down on the stalled shock. The material falls back onto the core, feeding the growing black hole. Instead of a spectacular supernova visible across half the galaxy, you get a failed supernova, a cosmic anticlimactic ending where the star just disappears. The stellar mass black hole discovery suggests that the universe has multiple pathways to create these objects, multiple routes by which matter can be transformed from shining star to invisible gravitational well. Some stars die screaming in supernova glory, their deaths visible across cosmic distances. Others whisper their way into oblivion, collapsing quietly, leaving no trace except a gravitational presence where a star used to shine. But the result, in both cases, is the same: a region of spacetime so warped that it becomes disconnected from the rest of the cosmos, a one-way gateway that light and matter can enter but never leave. These stellar mass black holes, whether formed through supernova or direct collapse, represent just one population in the cosmic landscape. They're the ones we understand best because we can watch the progenitor stars and sometimes witness their transformation. But they're not the most massive, nor the most influential for understanding why black holes exist fundamentally. To grasp that, we need to look beyond individual stellar deaths toward objects millions or billions of times more massive, objects that sit at the hearts of galaxies. Objects that challenge our understanding of how structures can grow so large in a universe only 14 billion years old. But first, we need to understand what black holes actually are in the language of mathematics. Black holes aren't just collapsed stars. They're solutions to equations, precise mathematical descriptions of how space-time responds to concentrated mass and energy. The story begins in 1915 when Einstein published his general theory of relativity. At its core, general relativity makes a revolutionary claim. Gravity isn't a force pulling across empty space. Gravity is geometry. Mass and energy curve spacetime itself, and objects moving through this curved geometry follow paths we interpret as gravitational attraction. Einstein summarized this relationship in his field equations, 10 coupled nonlinear partial differential equations that relate the curvature of spacetime to the distribution of mass and energy within it. The equations are compact and elegant when written in the language of tensor calculus, but they encode incredible complexity. Solving Einstein's equations for any but the simplest situations requires sophisticated mathematical techniques or numerical computation. Yet within months of Einstein publishing his theory, while World War I raged across Europe, a German physicist named A. German physicist found the first exact solution to Einstein's field equations. Schwarzschild was serving in the German army on the Russian front, calculating artillery trajectories by day. In whatever spare moments he could find, by candlelight in his tent, he was working through the mathematical implications of Einstein's new theory. He was dying of a rare autoimmune disease contracted at the front, his skin blistering and peeling, in constant pain. Yet he pushed through to find what Einstein himself had not been able to derive, the exact mathematical description of spacetime around a spherically symmetric mass. What Schwarzschild discovered was the solution for a perfectly spherical, non-rotating mass in an otherwise empty universe. This solution describes the geometry of spacetime around any spherically symmetric object, from a planet to a star to something far stranger. The mathematics was elegant, surprisingly simple compared to the complexity of Einstein's full equations. The solution contained a parameter, now called the Schwarzschild radius, that appeared to mark a special surface where the metric coefficients in the equations seemed to diverge, where certain terms became infinite. This radius, which would later be recognized as the event horizon, is proportional to the mass of the object. For our Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. For a person weighing 70 kilograms, it would be about 10 to the negative 25th meters, far smaller than an atomic nucleus. These numbers represent the size to which these objects would need to be compressed for their gravitational field to become so intense that light could not escape. Schwarzschild sent his solution to Einstein in December 1915, just weeks after the publication of General Relativity. Einstein was amazed that an exact solution had been found so quickly. He presented Schwarzschild's work to the Prussian Academy of Sciences in January 1916. Schwarzschild, tragically, died in May 1916, never living to see how profoundly his solution would shape our understanding of the universe. He was 42 years old. At the time, this seemed like a pure mathematical curiosity. After all, the Sun is currently about 696,000 kilometers in radius, far larger than its Schwarzschild radius. Earth is about 6,371 kilometers in radius, immensely larger than 9 millimeters. The Schwarzschild radius represented a theoretical limit, a mathematical possibility that nature surely never realized. Or so physicists thought. For decades, the scientific community largely ignored or misunderstood the implications of the Schwarzschild solution. Einstein himself was skeptical that nature would permit such extreme objects to form. Some physicists argued that the apparent singularities in the equations were artifacts of the coordinate system Schwarzschild had chosen, mathematical illusions rather than physical realities. It wasn't until the 60s, nearly 5 decades after Schwarzschild's original work, that physicists fully understood what his solution was telling them. The Schwarzschild radius represents a genuine surface in spacetime, a one-way membrane. An object that crosses inward through this radius can never return to the external universe. Light emitted from within is trapped, unable to climb out of the gravitational well. An observer watching something fall toward this surface would see it slow down, redden, and fade, asymptotically approaching but never quite crossing in the external observer's time frame. But from the perspective of the falling object, something remarkable happens. The surface passes without incident. No wall, no barrier, no physical demarcation. Just smooth continuation of the journey inward, with one critical difference: all paths now lead deeper in. Every direction that was previously outward now points inward. Even light, even particles traveling at maximum speed cannot move outward from within. The geometry has become so warped that outward ceases to be a meaningful direction. This is what defines a black hole in general relativity, not the absence of matter, but the presence of an event horizon, a boundary in space-time beyond which events cannot influence the external universe. The Schwarzschild solution describes the simplest possible black hole, non-rotating, uncharged, existing in an otherwise empty universe. But black holes in nature are more complicated. In 1963, a mathematician found the solution for a rotating black hole, which describes the vast majority of black holes we expect to find in the actual universe. A rotating black hole drags space-time around with it, creating a region called the ergosphere, where nothing can remain stationary with respect to distant observers. We'll return to the strange properties of rotating black holes later. In 1965, Penrose proved a theorem that had profound implications for understanding black holes. He showed that once an event horizon forms, the formation of a singularity inside is inevitable, at least according to classical general relativity. This singularity, a point where space-time curvature becomes infinite and the equations of general relativity break down, represents the ultimate failure of our current theories to describe what happens at the very center of a black hole. These mathematical discoveries led to what physicists call the no-hair theorem, a principle stating that black holes are remarkably simple objects. Once a black hole forms, according to this theorem, it can be completely described by just three numbers: its mass, its electric charge, and its angular momentum. All other information about the matter that formed the black hole, what it was made of, how it was arranged, what its history was, all of that is lost behind the event horizon, irrelevant to the external universe. A black hole has no hair, no complex structure, just these three fundamental properties. This simplicity is both elegant and disturbing. It suggests that black holes are the ultimate information destroyers, erasing all details about their formation and evolution. This leads directly to the information paradox we'll explore later, one of the deepest puzzles in theoretical physics. But there's another principle that emerged from this mathematical exploration, something called cosmic censorship. This conjecture, proposed by Penrose, suggests that nature never allows a naked singularity, a singularity without an event horizon, to form in the real universe. If cosmic censorship is true, then singularities are always cloaked behind event horizons, always hidden from the external universe, unable to causally affect anything outside their light cone. The universe, in essence, censors its own most extreme pathologies, preventing them from disrupting the orderly evolution of space and time beyond. These mathematical insights paint a picture of black holes, not as mysterious cosmic monsters, but as inevitable consequences of general relativity. If you accept Einstein's description of gravity as space-time curvature, if you accept that matter can be compressed to high enough densities, then black holes must exist. They're not optional. They're not cosmic accidents. They're mathematical necessities required by the very structure of space-time itself. The equations are deterministic. Given the physics we observe, black holes are unavoidable. And if we accept this mathematical inevitability, we can shift our question from whether they exist to what role they play in cosmic evolution. What would the universe be like without them? To answer that, we need to look beyond individual black holes toward the massive giants that lurk at the centers of galaxies. Objects so large and so influential that they shape the evolution of entire galactic systems over billions of years. Nearly every large galaxy harbors a supermassive black hole at its center. These aren't stellar mass remnants, but monsters weighing millions to tens of billions of solar masses. The black hole at the center of our own Milky Way, called Sagittarius A star, weighs about 4 million times as much as our Sunday. The black hole at the center of the nearby Andromeda galaxy is roughly 100 million solar masses. And at the extreme end, Black holes like the one at the center of the galaxy M87, which we'll discuss shortly, or some black holes, weigh billions of solar masses. To put these numbers in perspective, if you could somehow compress our entire solar system, the Sun and all the planets and all the asteroids and all the comets and everything within the outer reaches of the Kuiper Belt, down to its Schwarzschild radius, you'd create a black hole only a few kilometers across. The supermassive black hole in M87, by contrast, has an event horizon larger than our entire solar system. Its Schwarzschild radius is about 20 billion kilometers, large enough to encompass the orbits of all the planets out to Neptune. These objects are so massive, so influential, that they completely dominate the gravitational dynamics in the central regions of their host galaxies. Stars in the very center of our Milky Way orbit Sagittarius A star at tremendous speeds, completing orbits in just years or decades, despite being light years away from the black hole. By carefully tracking the motion of these stars over years and decades, astronomers have been able to precisely measure the mass of Sagittarius A star and confirm that it's indeed a supermassive black hole, not some other exotic object. But here's the problem. We don't know how these supermassive black holes formed. The stellar mass black holes we discussed earlier have clear origins. They're remnants of massive stars that exhausted nuclear fuel and collapsed. We can calculate the details, simulate the process, sometimes observe the supernovae that create them. Supermassive black holes. Different story entirely. Even the most massive stars only create black holes of perhaps 100 solar masses. To build a billion solar mass black hole, you'd need to somehow combine millions of stellar mass black holes or find another mechanism entirely. And there's a timing problem that's become more acute in recent years. The universe is approximately 13.8 billion years old. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has been peering into the early universe, observing galaxies as they appeared when the cosmos was only a few 100 million years old, less than 5% of its current age. And JWST is finding supermassive black holes in these early galaxies, black holes weighing millions or even billions of solar masses, already formed and already actively accreting matter when the universe was incredibly young. One discovery particularly stunned astronomers. A black hole in a galaxy called a galaxy that existed when the universe was only about 570 million years old, yet already weighed several million solar masses. Another, in the galaxy, another galaxy, appears to be about 2 million solar masses at a time when the universe was only 420 million years old. These aren't isolated cases. JWST is finding supermassive black holes throughout the early universe, suggesting they're common rather than rare. How? How did these objects grow so massive so quickly? The growth of black holes is limited by physics. As matter falls into a black hole, it heats up in the accretion disk, creating radiation that pushes outward against further infall. There's a theoretical maximum rate called the Eddington limit, determined by the balance between gravitational attraction and radiation pressure. Growing at the Eddington limit, a stellar mass black hole of, say, 30 solar masses would take hundreds of millions of years to reach 1 million solar masses, and billions of years to reach 1 billion solar masses, assuming continuous accretion, which is unlikely. Yet, JWST shows us billion solar mass black holes that formed in a few 100 million years. The math doesn't add up unless something unusual was happening. Either these black holes were somehow growing faster than the Eddington limit through particularly efficient accretion or unusually dense gas streams, or they started from seeds much more massive than stellar mass black holes, or there's some formation mechanism we haven't yet discovered or fully understood. One possibility is that in the early universe, massive gas clouds collapsed directly into black holes without ever forming stars first. If you have a sufficiently large, dense cloud of pristine hydrogen and helium, and if you can prevent it from fragmenting into smaller pieces, it might collapse as a single object, forming a black hole of perhaps 10,000 or even 100,000 solar masses in one fell swoop. These seed black holes could then grow more rapidly, reaching supermassive status within the time constraints JWST is imposing. Another possibility involves the collision and merger of smaller black holes. In dense stellar environments like the cores of young galaxies, stellar mass black holes might form in great numbers and then sink to the center through a process called dynamical friction, eventually merging together to build more massive objects. This process might be accelerated if these early galaxies were much more compact and dense than galaxies today, allowing black holes to find each other and merge more efficiently. We don't yet know which of these mechanisms, or which combination of them, operated in the early universe to create the supermassive black holes we observe. It remains one of the most active areas of research in astrophysics, with JWST data continuing to challenge and refine our theories. But however they formed, once supermassive black holes established themselves at the centers of galaxies, they began to shape the evolution of those galaxies in profound ways. In 2024, an astrophysicist published work on what he calls the co-evolution model of galaxies and black holes. The idea isn't entirely new. Astronomers have known for decades that there are correlations between black hole masses and galactic properties, but this work synthesizes observations from multiple wavelengths and provides a detailed picture of the feedback mechanisms at play. The idea is that supermassive black holes and their host galaxies don't just coexist. They actively regulate each other's growth through a feedback loop that has been operating for billions of years, shaping the universe we observe today. Here's how it works. As a supermassive black hole accretes matter, the matter doesn't fall directly into the event horizon in a smooth, quiet flow. Instead, it spirals inward through an accretion disk, a swirling maelstrom of superheated gas orbiting the black hole at tremendous speeds, often significant fractions of light speed. Friction in this disk, as particles collide and magnetic fields tangle and reconnect, heats the gas to millions of degrees, causing it to radiate enormous amounts of energy across the electromagnetic spectrum, from radio waves to X-rays. This radiation, along with powerful jets of material that are launched perpendicular to the accretion disk by complex magneto-hydrodynamic processes we're still working to fully understand, carries energy outward into the surrounding galaxy. This energy doesn't just radiate harmlessly into space. It interacts with gas in the galaxy, heating it, pushing it around, sometimes even expelling it entirely from the galaxy in powerful winds moving at thousands of kilometers per second. When a supermassive black hole is actively feeding, we call it an active galactic nucleus, or AGN. The most powerful AGN can outshine their entire host galaxy by factors of hundreds or thousands, blazing with the light of trillions of suns visible across billions of light years, so bright They were once mistaken for nearby stars when first discovered in the 60s. But this incredible energy output has consequences for the host galaxy. The radiation and jets from an AGN can heat the surrounding gas to such high temperatures, tens of millions of degrees, that it can't cool down and collapse to form new stars. The gas becomes too hot, too energetic. Its thermal motions prevent gravitational collapse. Essentially, an active supermassive black hole can shut down star formation in its host galaxy, preventing new generations of stars from being born, starving the galaxy of the fuel it needs to continue growing. This is the feedback mechanism. The black hole accretes gas, grows larger, becomes more active, heats more gas, suppresses star formation, which eventually reduces the amount of cold, dense gas available to fall into the black hole, which causes the black hole's activity to decline, which allows gas to cool over millions of years and star formation to resume, which eventually channels more gas back into the central regions through gravitational torques and stellar winds and supernovae, reactivating the black hole, starting the cycle anew. It's a self-regulating cycle that operates over tens to hundreds of millions of years, and it appears to function in galaxies throughout the universe. Observations show a tight correlation between the mass of supermassive black holes and properties of their host galaxies, particularly the mass of stars in the central bulge. This correlation, known as the M-sigma relation, shows that black hole mass scales with the velocity dispersion of stars in the bulge. More massive black holes live in galaxies where stars are moving faster, indicating deeper gravitational potential wells. This correlation is so tight that you can predict a galaxy's central black hole mass to within a factor of a few just by measuring how fast stars are moving hundreds of light years away from the black hole. The correlation holds across 4 orders of magnitude in black hole mass, from millions to tens of billions of solar masses, suggesting that black holes and galaxies have been influencing each other's growth throughout cosmic history. Without supermassive black holes, galaxies would be very different places. They might be more massive, since there would be no feedback to limit their growth. They might have much higher star formation rates, since there would be nothing to heat and expel the gas that fuels star birth. Or they might be more chaotic and unstable, lacking the regulatory mechanism that helps maintain galactic structure over cosmic time. In essence, supermassive black holes appear to serve as cosmic thermostats, regulating the temperature and density of gas in galactic centers, controlling the rate at which stars form, shaping the overall structure and evolution of galaxies. They're not passive passengers in galactic evolution. They're active participants, essential components of the cosmic ecosystem. This brings us to April 2019. When the Event Horizon Telescope collaboration released the first direct image of a black hole, capturing the supermassive black hole at the center of M87. The image shows a bright ring of glowing gas surrounding a dark central region, the shadow of the event horizon itself. That shadow is enormous, about 40 billion kilometers across, larger than our entire solar system. The bright ring is the accretion disk, gas swirling around the black hole at nearly light speed, heated to billions of degrees. This image represents significant technical achievement. M87 is 55 million light-years away. The black hole's event horizon, despite being billions of kilometers across, subtends an angle on the sky of only about 20 micro-arcseconds, roughly equivalent to observing a grape on the lunar surface from Earth. To achieve this resolution, the EHT team created a virtual telescope the size of Earth itself, linking radio dishes worldwide through very long baseline interferometry. The M87 image and a subsequent image of Sagittarius A star released in 2022 mark the beginning of direct black hole observation. We're no longer just inferring existence from gravitational effects. We're observing them, mapping their shadows, studying material dynamics in their immediate vicinity, testing general relativity in the strongest gravitational fields accessible to observation. These supermassive giants shape galactic architecture, regulate star formation, influence matter distribution across vast regions. They're woven into galactic structure, as fundamental to galactic evolution as stars and gas and dark matter. Yet, as important as they are individually, black holes reveal perhaps their deepest secrets not in isolation, but in pairs when two massive objects spiral together and merge in the most violent events since the Big Bang. To understand this aspect, we need to discuss ripples in spacetime. We need to talk about gravitational waves. For most of human history, astronomy was a visual discipline. We observed the heavens with our eyes, then with telescopes, then with detectors sensitive to wavelengths beyond visible light, from radio waves to gamma rays. But always, we were observing electromagnetic radiation, photons traveling through space, light in all its forms. General relativity predicted something different, a fundamentally new way to observe the universe. According to Einstein's theory, accelerating masses create ripples in the fabric of spacetime itself, distortions that propagate outward at the speed of light, carrying energy and information about the events that created them. Einstein called these ripples gravitational waves. But Einstein himself was skeptical that gravitational waves would ever be detected. They're extraordinarily weak. A gravitational wave passing through your body would compress you in one direction while stretching you in a perpendicular direction by an amount far smaller than the diameter of an atomic nucleus. The effect is real, but detecting it requires measuring changes in distance of less than 1 part in 10 to the 21st power. It's like trying to measure the distance from Earth to the nearest star to an accuracy smaller than the width of a human hair. For decades, detecting gravitational waves seemed impossible. But in the 70s and 80s, physicists developed a concept for an instrument sensitive enough to do the job: a laser interferometer, an L-shaped detector with arms several kilometers long. A passing gravitational wave would alternately stretch one arm while compressing the other, creating a tiny interference pattern in the laser light traveling through the arms. By making the arms as long as possible and using extremely precise laser measurements, such an instrument might just barely be sensitive enough to detect gravitational waves from the most violent events in the universe. The United States built 2 such detectors, located in Louisiana and Washington State, collectively called LIGO, the Laser Interferometer Gravitational Wave Observatory. Each detector has arms 4 kilometers long, maintained in an ultra-high vacuum, with mirrors suspended by elaborate isolation systems to shield them from vibrations, temperature fluctuations, and every other source of noise imaginable. LIGO began operation in the early 2000s, but initially detected nothing. The universe, it seemed, was quieter in gravitational waves than hoped, or the detectors weren't yet sensitive enough. So the collaboration shut down the detectors and spent several years upgrading them, improving the lasers, enhancing the isolation systems, increasing the sensitivity by a factor of 10. Advanced LIGO came online in September 2015, Within days, it detected something. On September 14, 2015, both LIGO detectors registered a signal, a chirp lasting only a fifth of a second, increasing in frequency and amplitude before cutting off abruptly. The two detectors, separated by 3,000 kilometers, recorded nearly identical signals, offset in time by the light travel time between them, confirming this was a real signal passing through Earth, not local noise. The signal matched theory perfectly for two black holes spiraling together and merging. Two black holes, weighing approximately 36 and 29 solar masses, had been orbiting each other, gradually drawing closer as they radiated energy in gravitational waves. In their final moments, they orbited each other hundreds of times per second, traveling at significant fractions of light speed, creating space-time distortions strong enough to detect across over 1 billion light-years. The merger itself released more power than all the stars in the visible universe combined for that brief instant. 3 solar masses worth of energy was converted into gravitational waves, pure geometry radiating outward through space-time. The final black hole, weighing 62 solar masses, was less massive than the sum of its progenitors. The missing 3 solar masses had been transformed into the gravitational wave energy that LIGO detected. This event, designated this first detection, confirmed a century-old prediction of general relativity. Gravitational waves are real. Space-time itself can carry information. The universe can be observed not just through light, but through geometry itself. And it confirmed something else. Binary black holes exist, and they merge. Prior to this detection, we had observed binary neutron stars and systems where a black hole orbited a normal star, but never 2 black holes orbiting each other. This first detection proved that such systems form and evolve to the point of merger. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Each one provides new information about black hole populations, about how binary systems form and evolve, about the behavior of space-time in strong gravitational fields, about whether general relativity holds up in the most extreme conditions we can observe. But one detection stands out as particularly puzzling and important. On November 23, 2023, the detectors registered a signal from the merger of 2 black holes weighing approximately 140 and 103 solar masses. The final black hole weighed about 233 solar masses. 10 solar masses worth of energy, more than in this first detection, was released in gravitational waves. The reason this detection is significant has to do with stellar evolution theory. Remember the process we described earlier, how massive stars fuse elements up to iron and then collapse. There's a complication we didn't mention. For stars in a particular mass range, roughly between about 65 and 130 solar masses at the time of core collapse, something different happens. In these stars, the core becomes so hot that photons in the core have enough energy to spontaneously create electron-positron pairs. This pair production removes energy from the core, causing the pressure to drop, which allows the core to contract further. The contraction heats the core, which leads to explosive oxygen burning, which creates pressure that causes the core to expand. The expansion cools the core, which reduces pair production, which restores pressure, which allows the core to contract again. The star becomes unstable, pulsating violently. Eventually, the pulsations become so extreme that the star tears itself completely apart in what's called a pair instability supernova. No remnant is left behind. No black hole forms. The entire star is blown to smithereens, scattered across space. This process creates a gap in the mass spectrum of black holes. Theory predicts that black holes formed from stellar collapse should not exist with masses between about 65 and 130 solar masses. This is called the pair instability mass gap. And yet a later detection features black holes with masses squarely in this gap. The 140 solar mass progenitor shouldn't exist according to our understanding of stellar evolution. There are several possible explanations. Perhaps these black holes formed through hierarchical mergers, smaller black holes merging to create larger ones, then those merging to create even larger ones, bypassing the mass gap through multiple generations of mergers. Perhaps our understanding of pair instability supernovae is incomplete, and there are stellar evolution pathways we haven't fully accounted for that allow some stars in this mass range to collapse directly to black holes. Or perhaps these black holes formed through some exotic mechanism in the early universe, primordial black holes that have nothing to do with stellar collapse. We don't yet know, but detections like a later detection are forcing us to revise and refine our theories, to consider new possibilities, to recognize that the black hole population in the universe is richer and more complex than we previously imagined. Gravitational wave astronomy is still in its infancy. LIGO and Virgo detect black hole mergers out to a few billion light-years, sampling only a small volume of the universe. Future detectors like LISA, the Laser Interferometer Space Antenna, will observe from space, detecting lower-frequency gravitational waves from supermassive black hole mergers occurring across cosmic time. LISA will be able to observe black holes with masses millions to billions of times the Sun, watching them spiral together over months or years, mapping their orbital dance in exquisite detail. These observations will tell us how supermassive black holes grow, how often they merge, how galaxies interact and evolve. They'll provide a complete census of black holes across cosmic history, from the smallest stellar remnants to the most massive monsters in the universe. And they'll allow us to test general relativity in regimes that are currently inaccessible. When two black holes merge, space-time itself becomes dynamically warped, curved in ways that change rapidly, creating conditions that cannot be reproduced in any laboratory on Earth. By observing these mergers through gravitational waves, we can check whether general relativity accurately describes spacetime even in these extreme conditions, or whether modifications to Einstein's theory are needed. So far, general relativity passes every test. The gravitational waves we observe match theoretical predictions with extraordinary precision, but we're still early in this new era of observation. As our detectors become more sensitive, as we observe more mergers at greater distances and with higher masses, we may yet find deviations, hints that general relativity is an approximation of something deeper. Gravitational waves have given us a new sense for observing the universe, a way to hear the sounds of space-time itself. And what we're hearing is a cosmos filled with black holes colliding and merging, releasing energy in bursts that echo across billions of light years. These events aren't rare cosmic curiosities. They're common, occurring somewhere in the universe, perhaps once every few minutes. Black holes aren't isolated, unchanging objects. They're dynamic, interactive, evolving. They form from stellar collapse or direct collapse or primordial density fluctuations. They grow by accreting matter and by merging with each other. They shape galaxies and regulate star formation, and eventually, after timescales we'll explore later, they might even evaporate away completely, returning their energy to the universe. We need to address a problem that has troubled physicists for nearly 50 years. A conflict so deep it strikes at the foundations of everything we understand about reality. It's called the black hole information paradox, and it represents a clash between two of the most successful theories in science, general relativity and quantum mechanics. Let me explain the problem step by step, because it's both subtle and revolutionary, touching on the deepest principles of quantum theory. Imagine you have a book, a physical book, with words printed on paper. This book contains information, patterns of ink molecules arranged in meaningful sequences, forming letters, words, sentences, conveying ideas. Now, suppose you throw this book into a fire. The book burns, the paper turns to ash and smoke, the ink molecules break apart and disperse into carbon dioxide and other combustion products. The book, as a physical object, is destroyed, reduced to scattered atoms and molecules and photons. But according to the principles of quantum mechanics, the information in the book isn't actually destroyed. The precise quantum state of every particle that made up the book, the exact arrangement of molecules, the specific positions and momenta of every atom, the quantum numbers of every electron, all of that information is preserved in the quantum state of the smoke and ash and heat and light. The information has been scrambled, made practically inaccessible, spread across countless particles dispersing into the environment, but it's not destroyed. In principle, if you could measure the quantum state of all the combustion products with perfect precision, if you knew the exact trajectory and polarization of every photon emitted, the exact position and velocity of every molecule of smoke, the exact quantum state of every ash particle, and if you had godlike computational ability to run the equations backwards, you could reconstruct the original quantum state of the book. You could, in a sense, unburn the book, at least in principle. This principle is called unitarity, and it's absolutely fundamental to quantum mechanics. Quantum evolution is described by unitary operators, mathematical transformations that preserve probability. Quantum information is never truly destroyed in any physical process. It can be scrambled, spread out, made inaccessible in practice, but it's always preserved in principle. The quantum state of a closed system evolves deterministically according to the Schrödinger equation, and that evolution is time reversible. If unitarity were violated, if information could be genuinely destroyed, then the mathematical framework of quantum mechanics would fall apart. Probabilities wouldn't add up to 1. You could create energy from nothing. Causality could be violated. The entire logical edifice of quantum theory, tested to extraordinary precision in countless experiments, would collapse. Now let's consider what happens when you throw that book into a black hole instead of a fire. According to classical general relativity, the book crosses the event horizon and falls toward the singularity at the center. From the perspective of an external observer, the information in the book is now completely inaccessible. No signal can escape from inside the event horizon. The information has effectively been removed from the universe, sequestered behind a one-way membrane. But here's where things get interesting. In 1974, Hawking made a crucial discovery. He showed that when you apply quantum mechanics principles to black holes, something unexpected happens. Black holes aren't completely black. They emit radiation. The mechanism is subtle, rooted in quantum field theory. Quantum mechanics tells us that empty space isn't truly empty. Even in a perfect vacuum, quantum fields are always there, fluctuating. Virtual particles, particle-antiparticle pairs, spontaneously appear and then annihilate each other in time frames shorter than could ever be measured directly. These virtual particles exist in a quantum gray area, borrowing energy from the vacuum for brief instants allowed by Heisenberg's uncertainty principle before paying it back. They're real enough to have measurable effects. They contribute to the Lamb shift in atomic spectra. They create the Casimir force between conducting plates, but they're not particles in the usual sense. Near the event horizon, something can happen to these quantum fluctuations that transforms them from virtual to real. A particle-antiparticle pair can appear just outside the horizon. Ordinarily, they would quickly annihilate. But if they appear close enough to the event horizon, something else can occur. One particle falls across the horizon before annihilation can happen, while the other escapes to infinity. From the external universe's perspective, this appears as if the black hole has emitted a particle. The escaping particle becomes real, carrying positive energy away from the black hole. The infalling particle, from an external perspective, can be thought of as carrying negative energy. It reduces the black hole's mass-energy content. The black hole has radiated, losing a tiny amount of mass in the process. The temperature of this radiation is inversely proportional to the black hole's mass. Small black holes are hot, massive black holes are cold. The formula is elegant. The temperature in Kelvin is approximately 6 times 10 to the -8th power divided by the mass in solar masses. A 10 solar mass black hole has a temperature of about 6 nanokelvin. The 4 million solar mass black hole at the center of our galaxy has a temperature of about 15 femtokelvin, 15 millionths of a billionth of a degree above absolute zero. This process, now called Hawking radiation, means that black holes slowly evaporate. They emit thermal radiation, very cold radiation for large black holes, but genuine radiation nonetheless. And as they emit this radiation, they lose mass. Eventually, after an incomprehensibly long time for stellar mass or supermassive black holes, they would completely evaporate. For a solar mass black hole, the temperature of Hawking radiation is about 1/10 millionth of a degree above absolute zero. The evaporation timescale is about 10 to the 67th power years, far longer than the current age of the universe. For supermassive black holes, the timescales are even more extreme. But the principle is clear. Black holes aren't eternal. They have a finite lifetime, at least according to quantum theory. Here's the problem. Hawking showed that the radiation emitted by a black hole is purely thermal, completely random, containing no information about what fell into the black hole. It's like the random glow of any hot object, characterized only by temperature, with no structure that encodes the quantum state of the infalling matter. So what happens to the information in the book we threw into the black hole? According to Hawking's calculation, the information is destroyed. When the black hole finally evaporates completely, the information that fell in is gone, erased from the universe. Genuinely, irreversibly destroyed. But this violates unitarity. Quantum mechanics says information can't be destroyed. General relativity and Hawking's calculation say it is destroyed. One of these theories must be wrong, or incomplete, or there must be some way to resolve the contradiction. This is the information paradox. It's not just an esoteric puzzle for theoretical physicists to argue about. It's a fundamental crisis in our understanding of nature. If information is destroyed in black holes, then quantum mechanics is wrong in its most basic principles. If information is preserved, then we're missing something crucial about how black holes work, and our understanding of general relativity or quantum field theory must be incomplete. For decades, physicists struggled with this problem. Some argued that information is indeed destroyed, that we need to modify quantum mechanics to allow for information loss in extreme circumstances. Others insisted that information must be preserved somehow, that it's encoded in the Hawking radiation in ways too subtle to see in Hawking's original calculation. Still, others proposed more exotic solutions. Maybe the information escapes through wormholes, or is encoded on the event horizon itself, or leaks out through quantum tunneling effects. The debate was fierce, with luminaries of physics taking different sides. Hawking himself spent decades defending the view that information is destroyed, though he later changed his mind. A physicist famously bet Hawking and another physicist that information is preserved, a bet that Hawking conceded in 2004, though the method of preservation remained unclear. A major breakthrough came in 2019, when physicist and collaborators made important progress by carefully analyzing what's called the Page curve. This curve describes how the entropy of Hawking radiation should evolve over the lifetime of a black hole. If information is preserved, the curve should follow a particular shape, first increasing as the black hole evaporates, then decreasing as the information starts to emerge in the radiation. This work showed that by carefully accounting for quantum entanglement between the black hole and the radiation it emits, you can recover a Page curve consistent with information preservation. The information doesn't escape immediately. It remains encoded in subtle quantum correlations between the black hole and the radiation it has emitted. As the black hole continues to evaporate, these correlations become stronger, and eventually, after about half the black hole's mass has been radiated away, information begins to emerge in the Hawking radiation. This doesn't mean we fully understand how information escapes. We don't have a complete quantum theory of gravity that describes the interior of black holes and the evaporation process in detail. What this work shows is that within certain frameworks for thinking about quantum gravity, particularly those involving holographic principles that we'll discuss shortly, information preservation is possible and perhaps even natural. The information paradox remains officially unsolved. We don't yet have a universally accepted, complete resolution. But this work and related developments have shifted the consensus in the physics community toward believing that information is indeed preserved, that unitarity holds even for black holes, that we're not seeing the violation of fundamental quantum principles, but rather glimpsing hints of a deeper theory that unifies quantum mechanics and gravity. Black holes have temperature, they have entropy, they obey thermodynamic laws, and these thermodynamic properties hint at something startling about the nature of spacetime itself. Let's start with entropy. In everyday thermodynamics, entropy measures disorder, the number of microscopic configurations a system can have while maintaining the same macroscopic properties. A cup of hot coffee has lower entropy than the same coffee after it's cooled and mixed with the surrounding air. because there are more ways to arrange the molecules when they're dispersed and at room temperature than when they're concentrated and hot. In the 70s, a physicist proposed something radical. Black holes have entropy, and the entropy of a black hole is proportional not to its volume as you might expect, but to the area of its event horizon. Specifically, the black hole entropy is 1/4 of the horizon area measured in Planck units, where the Planck length is about 10 to the negative 35 meters, the tiny length scale where quantum gravitational effects become important. For a solar mass black hole, the entropy is enormous, about 10 to the 61st power. For a supermassive black hole weighing 1 billion solar masses, the entropy is about 10 to the 79th power. These are large numbers, vastly exceeding the entropy of any ordinary object with similar mass. This relationship between entropy and area was puzzling when this was first proposed. Why should entropy be proportional to area rather than volume? The answer might lie in the holographic principle, one of the most significant ideas to emerge from theoretical physics in recent decades. The holographic principle suggests that all information contained in a region of space can be encoded on the boundary of that region, much like a hologram encodes three-dimensional information on a two-dimensional surface. Applied to black holes, this means everything that falls in, all information about particles and fields and quantum states, might be encoded somehow on the event horizon itself. Think about that for a moment. The event horizon isn't a physical surface, it's a mathematical boundary in spacetime, a point of no return. Yet the holographic principle suggests this boundary encodes information about everything inside. The three-dimensional volume interior to the black hole is somehow described completely by information spread across its two-dimensional surface. If true, this has significant implications. It suggests spacetime itself might be emergent, that the three dimensions we experience might arise from more fundamental degrees of freedom that live on lower dimensional surfaces. The universe might be, in some deep sense, holographic, with the reality we perceive emerging from information encoded on distant boundaries. This isn't science fiction, it's a serious idea supported by calculations in string theory and other approaches to quantum gravity. The holographic principle has been demonstrated precisely in certain toy models of spacetime, and many physicists believe it will prove central to any complete theory that unifies quantum mechanics and gravity. Black holes also have temperature, the Hawking temperature we mentioned earlier. For a black hole, temperature is inversely proportional to mass. Tiny black holes are hot, massive black holes are cold. A solar mass black hole has a temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. The supermassive black hole at the center of our Milky Way has a temperature of about 10 to the negative 14th power Kelvin, incomprehensibly cold. But temperature implies thermal radiation, which is exactly what Hawking radiation is. And thermal radiation carries away energy, which means black holes cool down as they evaporate, following thermodynamic principles just like any hot object cooling in a cold environment. There's even a black hole analog of the second law of thermodynamics. Hawking proved in the early 70s that the total area of all event horizons in the universe can never decrease, at least in classical general relativity. When black holes merge, the area of the final black hole's horizon is greater than the sum of the areas of the merging black holes. This area increase theorem mirrors the second law of thermodynamics, which states that total entropy never decreases in isolated systems. When it was suggested black holes have entropy and Hawking calculated their temperature, it seemed like these might be just analogies, useful mathematical similarities without physical meaning. But over time, physicists realized these aren't analogies. Black holes genuinely have thermodynamic properties. They're thermal objects with real temperature and real entropy that obey the actual laws of thermodynamics. This realization transforms how we think about black holes. They're not just gravitational wells. They're thermodynamic systems with maximal entropy for their size. They're the most efficient information storage devices allowed by physics, packing the maximum possible information onto their horizons. They're endpoints of thermodynamic evolution, maximally disordered configurations of matter and energy. And this connects back to why black holes might exist. Perhaps they're the universe's way of maximizing entropy, of exploring the highest entropy states accessible to matter. When a star collapses to form a black hole, the entropy increases dramatically. A stellar mass black hole has far more entropy than the star that formed it. From a thermodynamic perspective, black hole formation is almost inevitable, driven by the same entropic principles that drive all irreversible processes in nature. The universe favors high entropy states. Given enough time, matter tends to arrange itself in configurations that maximize disorder while respecting conservation laws and physical constraints. Black holes represent the highest entropy configurations for highly concentrated matter. Their existence might be thermodynamically preferred, statistically favored by the same principles that cause hot coffee to cool and ice to melt and stars to burn their fuel. But there's a strange inversion here too. While black holes maximize entropy, they also hide it behind event horizons, rendering it inaccessible to external observers. The interior of a black hole, if it has any structure at all, is invisible. All the complexity and disorder that the entropy represents is cloaked, hidden from view. This might be telling us something about the relationship between information and gravity. Maybe information doesn't like to be too concentrated. Maybe when you try to pack too much information into too small a volume, space-time itself responds by forming a horizon that hides the information from the external universe. The holographic principle suggests there's a maximum information density, a limit to how much information can be accessible in a given region of space. Black holes might be what happens when you reach that limit. These thermodynamic insights reveal black holes as quantum statistical systems, not just geometric objects. They're governed simultaneously by the laws of general relativity, which describe their space-time geometry, and by the laws of quantum mechanics and thermodynamics, which describe their information content and thermal properties. They sit at the boundary between classical and quantum physics, between deterministic geometric evolution and probabilistic quantum behavior, between the macroscopic and the microscopic. They're Rosetta Stones for translating between different languages of physics objects that must be consistent with multiple frameworks simultaneously and therefore constrain how those frameworks can be unified. In this sense, black holes might exist because the universe requires bridges between different physical theories, objects that embody principles from general relativity and quantum mechanics and thermodynamics all at once. By existing, by having the properties they do, they reveal deep connections between these theories that might otherwise remain hidden. They're not accidents. their necessities, implied by the logical consistency of physics itself, unavoidable consequences of taking all our theories seriously and asking how they fit together. The universe couldn't maintain logical coherence without objects that connect gravity to quantum information in precisely the way black holes do. But we've been discussing black holes as if they're simple, characterized only by mass and perhaps electric charge. In reality, almost every black hole in the universe has another crucial property that dramatically changes its behavior and opens up even stranger possibilities. Almost every black hole spins. Until now, we've mostly discussed the simplest possible black holes, the Schwarzschild solutions we encountered earlier. These are non-rotating black holes, perfectly spherical, characterized only by their mass. But in the real universe, such black holes are probably vanishingly rare. The stars that collapse to form black holes are rotating. The gas that spirals into growing black holes carries angular momentum. Through every formation pathway, black holes are born spinning, and that spin fundamentally changes their geometry and behavior. In 1963, New Zealand a mathematician found the exact solution to Einstein's field equations for a rotating black hole. This mathematical solution, as it's now called, describes spacetime around a spinning mass, and it reveals phenomena far stranger than the Schwarzschild solution could ever hint at. A rotating black hole doesn't have just one defining radius. It has an event horizon, yes, but outside that lies another surface called the static limit, or outer boundary of the ergosphere, a region where space-time itself is dragged around by the black hole's rotation. This frame-dragging effect, predicted by general relativity for any rotating mass, is subtle around rotating planets and stars measurable but small. The Earth drags space-time around with it as it rotates, creating tiny precession effects in satellite orbits that have been precisely measured. Around a rotating black hole, this effect becomes extreme, dominant, overwhelming. Inside the ergosphere, which lies between the static limit and the event horizon, space-time rotates so rapidly that nothing can remain stationary with respect to distant stars, not even light. Everything is dragged along in the direction of the black hole's spin. An astronaut trying to hover at a fixed location would find themselves pulled into rotation no matter how powerfully their engines fired. They could point their rockets in any direction, full thrust, but they'd still be swept around the black hole like a leaf in a hurricane. The very geometry of space-time is in motion, and everything within this region must move with it. You can move faster or slower in the direction of rotation, but you cannot stand still, and you certainly cannot move opposite to the rotation fast enough to appear stationary to a distant observer. But here's what makes the ergosphere particularly remarkable compared to the event horizon. It lies outside the event horizon itself. The event horizon is a one-way surface, a point of no return. But the outer boundary of the ergosphere can be crossed in both directions. You can enter the ergosphere and, with sufficient energy expenditure, escape back out. You're not doomed the moment you cross the static limit. You're just subject to this intense frame, dragging effect that forces you to rotate with the black hole. This creates a bizarre possibility first pointed out by Penrose in 1969, a mechanism so counterintuitive it seemed almost magical when first proposed. Suppose an object enters the ergosphere on a carefully calculated trajectory. Inside the ergosphere, It splits into two pieces, perhaps a spacecraft jettisons, some cargo, or a particle decays into two daughter particles. One piece falls into the event horizon, taking negative energy from the perspective of an external observer. Yes, negative energy. Inside the ergosphere, certain trajectories have negative energy relative to infinity, meaning that an object following such a trajectory contributes negatively to the total mass energy of the system. The other piece escapes the ergosphere, carrying more energy than the original object had. Where did this extra energy come from? From the black hole's rotation. The black hole has slowed very slightly, its angular momentum decreased, and that rotational energy has been converted into the kinetic energy of the escaping piece. The Penrose process provides a mechanism for extracting energy from rotating black holes, and it's not just a theoretical curiosity. Nature might actually use this process. In principle, you could extract up to 29% of a maximally spinning black hole's mass energy through this mechanism, far more efficient than nuclear fusion, which converts less than 1% of mass to energy. Advanced civilizations could theoretically use rotating black holes as power sources, lowering objects into the ergosphere on cables or firing particles in carefully calculated trajectories to extract rotational energy, harvesting the spin of black holes to power their civilizations. The physicist Roger Penrose, who first proposed this mechanism, and who later received the Nobel Prize for his work on black holes, once speculated that the jets we observe emanating from active galactic nuclei might be powered by variants of this process, with magnetic fields playing the role of the splitting mechanism, extracting rotational energy from supermassive black holes and channeling it into twin beams of particles and radiation shooting away at nearly light speed. Whether any civilization will ever achieve such technological feats is speculation. But the fact that the mechanism exists at all reveals something profound about rotating black holes. They're not just gravitational wells, but potential energy reservoirs, stores of rotational energy accessible through carefully orchestrated interactions with their twisted space-time geometry. The geometry inside a rotating black hole is even stranger than outside. In a Schwarzschild black hole, the singularity at the center is a single point where space-time curvature becomes infinite. In a rotating black hole, the singularity is a ring, a one-dimensional loop where curvature diverges, and the ring singularity opens up mind-bending possibilities. According to the mathematics of the rotating black hole solution, you could, in principle, pass through the ring singularity without encountering infinite tidal forces. On the other side, you'd enter a region where the geometry of spacetime is completely different, where some quantities that are typically time-like become space-like and vice versa. Some interpretations of the rotating black hole solution suggest this interior region might connect to other universes or other regions of spacetime far from the black hole. These possibilities are almost certainly unphysical. Real black holes probably don't have perfect ring singularities. Quantum effects would likely smooth out the singularity in ways we don't yet understand. And even if the geometry predicted by the rotating black hole solution is accurate, the interior regions beyond the ring singularity are probably unstable, collapsing or changing in ways that prevent any passage through them. But the mathematical structure alone is revealing. It shows that rotating black holes have richer internal geometry than we might expect, that space-time can be twisted and connected in ways that seem to violate our intuitions about space and time and causality. These solutions, even if idealized, point toward the strangeness lurking in general relativity when pushed to extremes. Real astrophysical black holes span a spectrum of rotation rates. Some might be spinning slowly, barely distinguishable from Schwarzschild black holes. Others might be spinning near the theoretical maximum, where the event horizon shrinks to nearly touch the ring singularity and the ergosphere becomes enormous. The black hole in M87 that the Event Horizon Telescope imaged appears to be spinning, with estimates suggesting it rotates at a significant fraction of the maximum possible rate. Rotation affects the accretion disks around black holes. The frame dragging in the ergosphere influences how gas orbits, creating regions where orbits can be stable closer to the event horizon than would be possible around a non-rotating black hole. The jets that emerge from active galactic nuclei, those powerful streams of material shooting away from supermassive black holes at nearly light speed, are likely powered by extracting rotational energy through processes related to the Penrose mechanism, mediated by magnetic fields threading through the ergosphere. When rotating black holes merge, as detected by gravitational wave observatories, the final remnant spin depends on the spins and orbital angular momentum of the progenitors. LIGO and Virgo data are revealing that merging black holes have a range of spin values, some high, some low, providing clues about their formation histories and the environments where they evolved. Rotating black holes also connect to the information paradox in subtle ways. The frame dragging and ergosphere structure might provide mechanisms for information to escape that don't exist in non-rotating black holes. Some quantum gravity theories suggest that the Hare theorem might not hold exactly for rotating black holes, that subtle imprints of what fell in could persist in the space-time geometry in ways we haven't yet understood. But beyond all the technical details, the existence of rotating black holes reveals something essential about gravity and angular momentum. Rotation is preserved even in the most extreme gravitational collapse. A collapsing star doesn't just become a point mass, it becomes a spinning singularity. The rotational information survives the collapse, encoded in the geometry of the event horizon and ergosphere. This suggests that black holes aren't complete information erasers. Even in classical general relativity, before considering quantum effects, black holes preserve certain kinds of information, specifically their mass, charge, and spin. The universe doesn't allow complete erasure of these fundamental properties. There's a flaw, a minimum amount of information that must survive, no matter how extreme the collapse. Why might this matter for understanding why black holes exist? Because it shows that black holes are rule-following objects, constrained by conservation laws, subject to the same principles that govern all physical systems. They're extreme, yes, but they're not lawless. They don't violate conservation of angular momentum. They don't ignore thermodynamics. They don't escape the constraints that quantum mechanics imposes on information. They exist within the framework of physics, as natural consequences of physical law applied consistently to extreme conditions. Their existence might be necessary for maintaining the consistency and coherence of that framework across all possible conditions, from everyday scales to the most compressed, energetic, rotating configurations that matter and energy can assume. Black holes, occupy a unique place in human consciousness, serving as symbols and metaphors in ways other astronomical objects don't quite match. Galaxies are beautiful, neutron stars are exotic, supernovae are spectacular. But black holes have captured collective imagination differently. Perhaps it's the invisibility. In nearly every human culture across history, what cannot be seen carries symbolic weight. Black holes are the ultimate in invisibility, places where light itself is trapped. Or perhaps it's the threshold. Humans are drawn to points of no return, to irrevocable choices. The event horizon is the perfect metaphor for irrevocable change, for passing beyond the point where return is possible. In popular culture, black holes often represent danger, cosmic threats that could swallow Earth. This portrays, exaggerates actual risk. A solar mass black hole would have the same gravitational influence as our Sun, but captures something true about their nature. They are genuine thresholds where familiar rules break down. But black holes also represent puzzles to be solved, frontiers of knowledge. For physicists, they're irresistible precisely because they're extreme, because they force careful thinking about assumptions usually taken for granted. This dual nature, threat and opportunity, eraser and revelator, mirrors something in the human relationship with the unknown. We fear what we don't understand, yet we're driven to explore it. There's a philosophical dimension too. Black holes challenge fundamental intuitions about persistence and identity. When matter crosses an event horizon, it becomes causally disconnected from the external universe. In what sense does it still exist? If something cannot interact with anything outside itself, if it cannot send signals or exert influences except through its gravitational field, has it ceased to exist in any meaningful way? The Event Horizon Telescope image of M87, that luminous ring surrounding absolute darkness, is beautiful in a stark way. It's an image of pure geometry, of light bending around curved spacetime. For artists and writers, black holes have become symbols available for use in ways that transcend literal physics. They represent oblivion and transformation, endings and beginnings. They appear in science fiction as plot devices and metaphors, in poetry as images of loss or transcendence, in visual art as representations of cosmic power. In popular culture, black holes often represent danger, cosmic threats that could swallow Earth. This portrays, exaggerates actual risk. A solar mass black hole would have the same gravitational influence as our Sun, but captures something true about their nature. They are genuine thresholds where familiar rules break down. But black holes also represent puzzles to be solved, frontiers of knowledge. For physicists, they're irresistible precisely because they're extreme, because they force careful thinking about assumptions usually taken for granted. This dual nature, threat and opportunity, eraser and revelator, mirrors something in the human relationship with the unknown. We fear what we don't understand, yet we're driven to explore it. There's a philosophical dimension too. Black holes challenge fundamental intuitions about persistence and identity. When matter crosses an event horizon, it becomes causally disconnected from the external universe. In what sense does it still exist? If something cannot interact with anything outside itself, if it cannot send signals or exert influences except through its gravitational field, has it ceased to exist in any meaningful way? The Event Horizon Telescope image of M87, that luminous ring surrounding absolute darkness, is beautiful in a stark way. It's an image of pure geometry, of light bending around curved spacetime. For artists and writers, black holes have become symbols available for use in ways that transcend literal physics. They represent oblivion and transformation, endings and beginnings. They appear in science fiction as plot devices and metaphors, in poetry as images of loss or transcendence, in visual art as representations of cosmic power. But perhaps most significantly, black holes remind us of our scale in the cosmos. We are small, fragile, brief. The universe contains objects so massive they warp space-time itself, so powerful their mergers shake the universe with gravitational waves. So long-lived, they'll exist after our sun burns out and our planet is reduced to dust. This could be crushing, but it can also inspire. We small, fragile, brief creatures have figured out what black holes are. We've written equations describing them. We've built instruments detecting them across billions of light years. We've photographed their shadows. We've measured the ripples they create in space-time. Black holes exist on scales incomprehensible to everyday experience, yet we comprehend them. We reach across vast distances with mathematics and observation to understand objects we can never visit, can never touch, can, in some cases, barely detect. So, black holes exist, in part, to be understood. Not because the universe cares whether we understand it doesn't, but because we care. We are the observers, the questioners. We take the raw data of existence and construct understanding from it. In this sense, asking why black holes exist is also asking why we exist, why there are conscious beings capable of wondering about the universe. But there's one final aspect to explore, their ultimate fate. What happens to black holes in the deep future when all stars have burned out and the universe has cooled to near absolute zero? We've discussed how black holes form, grow, merge, and shape galaxies. But we haven't confronted their ultimate destiny. Despite seeming permanence, black holes are not eternal. Over timescales that dwarf the current age of the universe by incomprehensible factors, black holes evaporate, slowly radiating away their mass through Hawking radiation until they vanish completely. Let's put some numbers to this process because the timescales involved are genuinely mind-boggling, almost absurdly vast. A solar mass black hole, remember, has a temperature of about 60 nanokelvins, 60 billionths of a degree, above absolute zero, and radiates Hawking radiation at an incredibly slow rate. The power output is about 10 to the negative 28th watts, far less than the energy of a single photon arriving at Earth from a distant star, incomprehensibly feeble. At this rate, the time for a solar mass black hole to completely evaporate is approximately 10 to the 67th power years. Let me try to give you a sense of this number, though it's almost impossible to grasp intuitively. The universe is currently about 14 billion years old, roughly 10 to the 10th power years. The expected lifetime of the last stars that will ever form, small red dwarfs burning hydrogen at miserly rates, is about 10 trillion years, 10 to the 13th power years. The time until every stellar remnant has cooled to the background temperature of the cosmos is perhaps 10 to the 14th power years. The evaporation of a solar mass black hole takes 10 to the 67th power years. That's 10 to the 53rd power times longer than the lifetime of the last stars. If you tried to count seconds from now until a solar mass black hole evaporates, counting one number per second continuously, You'd need more time than has currently existed in the universe just to count to 10 to the 20th power, and you'd still have 10 to the 47th more orders of magnitude to go. You wouldn't even be a rounding error. You wouldn't even be close enough to the real timescale to qualify as a rounding error. To put it another way, the ratio between 1 second and the entire current age of the universe is vastly, incomprehensibly larger than the ratio between the current age of the universe and the evaporation time of a solar mass black hole. Our universe's age compared to black hole evaporation timescales is less significant than a single heartbeat compared to the age of the cosmos. For supermassive black holes, the timescales are even more extreme, almost comically so. A billion solar mass black hole, like those at the centers of large galaxies, would take approximately 10 to the 98th power years to evaporate. A trillion solar mass black hole, if such objects exist or form, would take 10 to the 108th power years. These numbers are so large that they almost cease to have meaning. They're timescales on which protons might decay if they're unstable at all. They're timescales on which the expansion of the universe will have carried all galaxies so far apart that no galaxy outside our local gravitationally bound group will be visible from any other, each island universe alone in an expanding void. Their timescales approaching the heat death of the universe, the final equilibrium state where all useful energy has been dissipated, all temperature gradients have been erased, and nothing interesting can happen anymore because there's no free energy available to power any process. In this deep future, black holes will be among the last structured objects remaining. After the stars have burned out, after planets have been destroyed or flung into interstellar space, after white dwarfs and neutron stars have cooled to the background temperature, black holes will persist. They'll be the dominant mass objects in the universe, wandering through the expanding void, occasionally merging when chance encounters occur, but mostly existing in isolation, slowly, imperceptibly evaporating. And eventually, even they will vanish. The final moments of a black hole's life are dramatic in a way the earlier stages are not. As a black hole loses mass through Hawking radiation, its temperature increases. Remember, temperature is inversely proportional to mass for black holes. So as the black hole gets smaller, it gets hotter and radiates faster, which makes it lose mass faster, which makes it hotter still. There's a runaway feedback process. In its final second of existence, a black hole that has already evaporated for 10 to the 67th years or more will suddenly flare to incredible temperature and luminosity, possibly releasing the energy equivalent of millions of nuclear bombs in a final explosive burst before disappearing completely. All that remains is an expanding sphere of thermal radiation, photons and particles carrying away the black hole's final mass energy, dispersing into the cosmos. And then there's nothing. No event horizon, no space-time curvature, no information locked behind any surface. Just radiation expanding through space, indistinguishable from any other thermal radiation in the universe. This raises questions about the ultimate fate of information. We've discussed the information paradox, whether information is preserved when matter falls into a black hole. If information is indeed preserved, encoded somehow in the Hawking radiation, then after the black hole completely evaporates, that information must be fully recovered in principle, scattered across the radiation. The universe maintains its quantum coherence. But consider the timescale required 10 to the 67th years or longer. Preservation of information is a technical statement about quantum evolution mathematics, not a practical statement about recoverability. The information might be preserved in principle while being utterly scrambled and dispersed beyond any possibility of reconstruction. This connects to broader questions about the arrow of time and entropy. Black holes form because entropy increases when matter collapses. But black holes also evaporate, returning their mass energy to the universe in highly entropic form. Over vast timescales, black holes might be transient features, important during certain epochs of cosmic evolution, but not final endpoints. Perhaps the universe cycles through phases. In the current epoch, matter clumps into stars and galaxies, and black holes form as byproducts of stellar evolution and galactic dynamics. In the far future, after stars have burned out, black holes dominate. And in the unimaginably distant future, after even black holes have evaporated, the universe might consist of nothing but low-temperature radiation expanding through space, approaching a state of maximum entropy and minimum temperature. Or perhaps not. Some cosmological models suggest the universe might continue to evolve in unexpected ways. Quantum fluctuations over timescales of 10 to the 10 to the 10 to the 100 power years or more, numbers so large they're almost meaningless, might give rise to new structures, new pockets of low entropy, perhaps even new universes nucleating through quantum tunneling events. Black holes, in these scenarios, are not eternal monuments, but temporary structures, patterns of matter and energy that exist for a time and then dissolve. Their timescales are vast compared to human experience or even to the lifetime of stars, but finite nonetheless when viewed against the ultimate sweep of cosmic time. This perspective changes how we think about the question of why black holes exist. They're not permanent features of the cosmos. They're phases in the evolution of matter and energy, important during certain epochs, dominant at certain stages, but eventually fading as the universe continues its relentless expansion and cooling. They exist because the laws of physics permit them during certain temperature and density regimes. They persist because they're stable on timescales relevant to stellar and galactic evolution. They shape the cosmos we inhabit because we live in an epoch when they're important. But from the perspective of ultimate cosmic time, they're temporary, as transient as stars or planets or galaxies themselves. Yet there's something poignant about this impermanence. Even the darkest, most extreme objects in the universe, objects that seem eternal and unchanging, have finite lifetimes. Nothing in this universe is truly permanent except the laws of physics themselves, and even those might vary or evolve in ways we don't yet understand. Black holes exist in a universe governed by time's arrow, by the increase of entropy, by the gradual spreading and cooling of energy across ever larger volumes of space. They're participants in this cosmic evolution, not exempt from it. They form, grow, merge, and eventually dissolve, contributing to the universe's journey from low-entropy initial conditions to high-entropy final states. And we, observers of black holes, exist in a particular epoch of this cosmic story. We live in a time when stars still shine, when galaxies still swirl, when black holes are forming and growing and shaping the structures around them. We live in an era of complexity and structure, far from both the hot, dense beginning and the cold, empty end. From this privileged position in time, we can look outward at black holes and ask why they exist, knowing that the answer involves not just formation mechanisms and mathematical necessity, but also cosmic timescales, entropic evolution, and the temporary nature of all structures in an expanding universe. So why do black holes exist? Perhaps because the universe, at this stage in its evolution, at these temperatures and densities, under these conditions, naturally creates them. And perhaps they'll continue to exist, shaping the cosmos and challenging our understanding, until the very slow tick of Hawking radiation counts down their final moments, uncountable eons from now. We've journeyed far together through the landscape of black hole physics, from stellar collapse to gravitational waves, from information paradoxes to rotating geometries, from galactic architecture to far future evaporation. We've explored these objects from multiple angles, through multiple lenses, seeing them as gravitational phenomena, quantum systems, thermodynamic objects, galactic regulators, cultural symbols, and temporary structures in cosmic evolution. Now, finally, we can return to our original question with the full weight of everything we've learned. Why do black holes exist? The answer is multifaceted, viewed through different lenses. Mathematically, black holes exist because they're inevitable. If space-time curves with mass and energy according to Einstein's field equations, then black holes must exist as solutions. They're mathematical necessities required by theoretical structure. Astrophysically, massive stars cannot support themselves indefinitely against gravitational collapse. Nuclear fusion provides temporary support, but fuel is finite. For the most massive stars, no known force can halt collapse once it begins. In galactic evolution, supermassive black holes at galactic centers shape star formation, influence structure, participate in feedback loops determining how galaxies grow and evolve. They're active participants organizing matter on the largest scales. Thermodynamically, black holes represent maximal entropy states for concentrated matter. When stars collapse to form black holes, entropy increases dramatically. The universe's evolution toward higher entropy naturally creates them. In quantum gravity and information theory, black holes reveal connections between geometry, information, and quantum mechanics. They're laboratories where our best theories conflict and where hints of deeper truths emerge. Cosmologically, black holes exist as temporary phases in matter and energy evolution. They form during certain epochs, dominate for vast timescales, and eventually evaporate as the universe continues expanding and cooling. All these answers are simultaneously valid, each revealing different aspects. The synthesis. Black holes exist because the universe operates according to consistent laws across all scales. The same geometric principles governing everyday phenomena also govern extremes. There's one set of rules, applied universally. Black holes emerge when you compress matter past every resistance, when you curve space-time to its limits, when quantum mechanics, general relativity, and thermodynamics must all work together. They're what happens when universal principles encounter extreme conditions. They're expressions of natural law, not violations. They demonstrate that physical rules work everywhere, maintaining consistency from quantum scales to cosmic scales, from gentle gravitational fields to warped space-time geometries. They exist because the universe is internally consistent. The cosmos continues its evolution above you. At this moment, black holes are forming from stellar collapse, merging in distant galaxies, accreting matter, warping space-time. Most remain invisible, known only through gravitational influence. Some blaze with tremendous luminosity as matter spirals inward. Others sit quietly, dormant. They're as integral to cosmic structure as stars that shine, planets that orbit, and space that stretches between galaxies. They're woven into reality's fabric, essential threads in the pattern that makes our universe what it is. You cannot see them, you cannot visit them. You will never approach an event horizon or witness a merger or watch as a black hole evaporates after timescales that reduce stellar lifetimes to heartbeats. But you can understand them. You can trace their existence from fundamental principles. You can comprehend why they must be, why the universe couldn't maintain logical coherence without them, why their existence is as natural and necessary as the existence of atoms, forces, and space-time itself. They exist in regions where space-time curves so drastically that light cannot escape. Places where familiar rules break down and new principles emerge. Places that shape galaxies and challenge physics and preserve information in ways we're still discovering. Black holes exist, not despite physical law, but because of it, because gravity is geometric, because mass warps space-time, because the equations allow, perhaps demand, that some configurations fold into themselves so completely that they become qualitatively different from ordinary matter. They're the universe processing what is into what will be. They're testing grounds where yesterday's matter becomes tomorrow's geometry. They're necessary, inevitable, consequential. And in their existence, they pose questions that echo through physics. What is real? What is knowable? What lies beyond current understanding? We may never have complete answers. But in asking in the human drive to explore, to question, to push against the limits of knowledge, we participate in something larger than ourselves, something that mirrors cosmic evolution itself. Black holes exist because the universe operates according to consistent principles applied across billions of years and infinite scales. And we exist, perhaps, to witness that consistency, to stand at the edge of the knowable and peer beyond, not with fear, but with curiosity, not with despair, but with comprehension. The black holes will continue their evolution long after humanity is gone. But for now, in this brief moment of cosmic time, we have the privilege of watching, of learning, of understanding the universe's most extreme gravitational expressions. Thank you for spending this time here. If this investigation has expanded your sense of what exists in our universe, I'm grateful you've been part of it.